Hello, Mr. Berry's geometry class. I'm looking at figures and cross sections assignments. You are only to do 6 through 11 and then draw nets for only 15 through 17. Do 24 and 27 through 30. Euler's formula is the faces plus the vertices equal the edges plus 2. This is due tomorrow, the 13th. So let's get on with it. For each polyhedron, how many vertices, edges, and faces are there, and list them. So for number 6, there are four vertices, and I have them listed there, and you could pause this. 6 edges, and I have them listed there, and 4 faces, and I have them listed there. Those are the triangles. There are 4 triangle faces. Go ahead and try 7 on your own as you pause this. And moving on to number 8, there are 10 vertices, and here they are, P through Y. 15 edges, and I have them, I think, all listed there. And take a look at all those. That's a Q there, because you can't read that. And then there are 7 faces. There are the 5 quadrilaterals and 2 pentagons that I have listed there. For number 9, I want to do 9 and 11, so I'm doing more than half of them for you. So even if you at least get these in, you're doing great. So faces plus vertices equals edges plus 2. We're using Euler's formula here. So we don't know the faces, so I leave it F. And I plug in everything else, the vertices and the edges. Vertices 9, edges 15. And then I just get F by itself. So F, the faces, equal 8. So there should be 8 for number 9. Try 10 on your own. For number 11, I'm looking for the V, the vertices. So I just get V all by itself. I subtract 20 from both sides, and I get 12. So there should be 12 vertices. Okay. For number 15, be careful of your art projects. They don't have to be, they don't have to be art projects. Be careful of your drawings. They don't have to be art projects. For 15, apply Euler's formula for each polyhedron, and then draw a net for this figure, for the 3-dimensional figure. So Euler's formula would have the faces plus the vertices equal the edges plus 2. And yep, it checks out. 11 equals 11, so that's good. And then this one, if I was to draw a net of 2-dimensional version of this, like, cut and flattened out, it would look like this. It doesn't have to be an art project, like I said. Try 16 on your own. 17, and you could have it look a little bit differently. This one, I opened it up from the top and spread it out. Notice it's a hexagon base. And then I have Euler's formula checking it out. 14 equals 14, so it does check out. For number 24, jumping over to 24, sketch a polyhedron where the faces are all rectangles and label the lengths of its edges. I didn't label the lengths, so I don't know. Let's go 2, 1. This ends up being 1, 2, 3, 4, 5, 6, 6, 1. So that would be 6, that would be 2, so on. Okay? So 2 different nets. This could be a net of it, and this could be a net of it. Okay, once again, not an art project by any means. Try 23 on your, or whatever else. No, 24, 27 through 30. So I have 27 and 29 for you. So 27 asks, suppose a number of faces in a certain polyhedron is equal to the number of vertices. Can the polyhedron have 9 edges? Explain. Well, no, because it must be even, not 9, not odd, or a 9 as the example, to satisfy Euler's formula here, okay? Because it would be 9 plus 2 if it had 9 edges. 9 plus 2 is 11, so you don't have something that you add up, 2 whole numbers that you would add up to get 11. So, you can't have half of a vertices, right? So, or half of a face, so that wouldn't work out. It'd have to be an even number. And then so for, try 28 on your own, 29. The plane contains the red edges of the cube. The red edge was here, and I have it drawn here. These are the red edges. You can see them in red. What plane could you draw out of that cube where the edges are red? Well, you would just have to do the diagonals. And that plane right there that I have in red would be an example of that. Okay? Try 30 on your own, and don't worry about making mistakes. Learn from them and correct them, and you're going to be doing well. Good luck.